Hi everyone, and welcome back to the session. Today we'll be touching on a very interesting topic called vector embeddings. And recently GPT has been taking the news by storm. And one of the key features that we can do with GPT is to augment it with some form of memory. And we can use vector embeddings to retrieve the relevant memories. So this is a very interesting topic and has a lot of potential. The recent model called Hugging GPT also uses something similar to do memory-augmented query. And I feel like this is really the way to go. This will lead to a lot of useful applications. I'm very sure Bing Search, the Microsoft search engine, uses something like this as well. Okay, so without further ado, let us begin. Today we have a special guest, Manas, who is an NTU freshman, and he develops amazing web apps. So without further ado, let me just invite him to share one of this Atomic Habits GPT. Manas, please.
Thanks, John, for having me. It's been a pleasure. So I'll perhaps maybe just give everyone a bit of an intro about myself, and then I can share the application that I built. So I'm Manas. I'm in NTU first year. I'm originally from India, and I enjoy building applications that are just fun and interesting, and I really like to dabble around in the machine learning space. So yeah, the idea of atomic, maybe I can share my screen. Is that, yeah, I can. Okay. Yeah, so the idea of a book GPT, or what we call a GPT book club, was initiated when I was reading this book, and I realized that, and usually this is true for a lot of self-help books. It's like they have maybe one or two core ideas, and the rest of the book is just examples and further elaborations on those core ideas. So I thought, is there a way you can kind of condense all of that information? And not only that, but also if you have a particular question that you're hoping to answer by reading the book, instead of reading the book and then trying to answer the question, can you just ask the question to the book? And there's this very interesting, there's this guy I follow on Twitter. His name is Makir Wrigley. I'm not sure if you guys have heard of him. Maybe I can just put a link of his Twitter in the chat. But he built something called Paul Graham GPT. Maybe I can just give you guys a quick or look into that. So the way it works is it's extracted on all of Paul Graham's essays, and you need, this is an open this thing, so you need to put in your OpenAPI key and stuff. But once you do all of that, you can ask any questions, and then it retrieves answers from Paul Graham's essays. So I realized that something similar can be done for a book, and that's what my friend and I did. We embedded an entire book. In fact, now we've embedded over 3 books. So we've done, I don't know why it's a bit slow right now, but we've done Atomic Habits, we've done The Psychology of Money, and we've also done How to Win Friends and Influence People. So maybe I can just give you an example on how Atomic Habits GPT works. So essentially what we're doing, if I had to explain the working, is for every single paragraph in the book, we're converting that into a vector using OpenAI's vector library. And we're storing that that vector database on, we should be storing it in Pinecone because that's what's used right now, but we're storing it on Supabase. We'll eventually port it to Pinecone. But what we're doing is, after we store it in Supabase, we have a user query. So let's say you have a question like how to stop procrastination, right? So when you ask a question like this to a book, essentially what you're trying to do is you're trying to find the passages in the book that are similar to what your question is trying to ask. So if I press enter now, what's happening in the backend is it's converting my question into a vector, and then it's comparing my query vector with every other vector in the book, and it's trying to find the most related paragraphs. And then we use ChatGPT to kind of summarize that entire response, and that's what's shown here. So you can say, this is what the final response is. And these are the most relevant passages from the book which talk about stopping procrastination. So that's one aspect of what my friend and I built. It's basically talking to a book. And I mean, you can extend this to absolutely anything. The most general version of this is a talk to a PDF. You have a PDF document. Essentially, the book that we embedded was a PDF, right? So you can just have your own PDF. It could be your school book. It could be absolutely anything, any piece of data. And it's the best control F that you can ever create. I think that's how we described it to a couple of people. So it's like if you want to find something in that PDF file, which is like maybe a couple of 100 pages long, but you don't really want to read through every single page of that, you just use something like an embedding and then vectors and find the most similar vectors. And I think John will also talk about how we do the vector comparison, which is using cosine similarity, but I think there are other metrics that you can use as well. Yeah, so that's on the site itself, the talk to the book part of the things. But we also have another side of this, which is a Notion template. So maybe I can quickly share my screen on that. Yep. So what we did over here is we ran ChatGPT over every single paragraph of the book. And we said, okay, for every chapter, we said come up with the top 5 ideas, and then we fed that entire chapter section by section to GPT, because also it has its context limit of 4,000 tokens and stuff. And then we generated all these different points in the book. So for example, if you go into chapter summary, you have the introduction chapter. These are the top 5 points. This chapter, there are again 5 points. Each chapter is collapsible. You can go in depth into the point. And the good thing about this is, I mean, what I envision to be the future of like reading would be, you buy something like this where you buy the template or you buy the book and the template, and you read a point like building identity based habits, but you don't necessarily understand what this means. So you just copy this and you put it back into the search and you say, hey, can you explain this a bit further with an example or something like that? And then GPT kind of summarizes everything, including context from the book itself. So it's an exciting space. And yeah, that's about what we're building on in terms of GPT Book Club. And I would say the best part about this is it's entirely reproducible, in the sense that it's entirely automated, sorry, in the sense that we can add another book. The only thing is we just need the PDF file. So we just take the PDF file, we embed the book, the search is ready, we run ChatGPT over the entire book, and we have something like the Notion template, which is also ready. And yeah, that's basically about the embedding capabilities of GPT. And people are doing some really cool stuff with this. Maybe just to end, I think John also might cover that in terms of these agent AIs, which I think is like the next frontier on what people are developing using GPT models. But I don't know if you played around with this thing called Auto GPT. So it to have, you have to have memory in its functionality. They also use embedding. So basically, whenever it comes up with some ideas, whenever it comes up with some text or whatever the user prompts it to, it stores all of that relevant information on Pinecone as an embedding. And when it's required later on, it just does a query search in that embedding, in the embeddings on Pinecone, and then retrieves the most relevant embeddings. So yeah, I think it's an exciting place that we're at right now. And embeddings, I mean, the rate of AI research is just growing so fast that embeddings is like probably 2 weeks old now. And although it sounds 2 weeks old, it's just very new. In the AI space, it's still yeah, it's basically 2 months have passed in the AI space. So yeah, maybe I'll just leave stop my screen share at that.
Can I ask a couple of questions?
Sure.
So first of all, yeah, brilliant work. I've been excited about trying something similar myself, actually. And this is really good for the scenario you speak of, which is information retrieval. So I have specific questions. I go and find all of the embeddings with, the lowest cosine distance or whatever, and then I do retrieval-augmented generation. So that's fine. But I'm more interested in the getting started phase, which is I almost want to be prompted with some high-level abstract information to seed the prompting process. So then I can ask specific questions. And I'm really interested in this idea of outlining. So let's imagine you've gone through the entire book, you've embedded all of the paragraphs. Is there a way of traversing that space dynamically using some kind of auto GPT? So for example, I could create this graph where I traverse all of the high level structure of the book. And then it almost starts by saying, well, here's the structure of the book. This is what it's about. Is there some kind of representation to capture the high level structure of the book just using that embedding space?
Oh, that's exciting. I think maybe I have 2 points to kind of not necessarily answer that question, because what your question is quite interesting, but maybe two suggestions. One is what we're already doing in terms of the Notion template, where we run ChatGPT. Basically, if I have to give you the exact details of what we're doing, we have chapter. So let's say the book Atomic Habits has 19 chapters, right? We take chapter 1 and we say, okay, we do clustering because everything is an embedding space. It's a vector now. So we use k-means clustering, and we say, okay, find the top 10 ideas in this book. And because maybe there are 20 paragraphs in chapter 1, but that's still big enough. That's still too big for ChatGPT's context window. So we say, find me the top 10 paragraphs, which have like some different distinct idea in them. And then we say, from those top 10, you find me the top 5. And that gives us the top 5 ideas for that chapter. So technically, in that sense, that could be the structure of that chapter, where it's like, okay, these are the top 5 points in that chapter. And you can kind of extend this idea to the entire book. So for example, when we're trying to find the top quotes in the book, now that's a harder problem to solve, because you may not have a top quote from every single chapter. So what we do is, in every chapter, we say, okay, if you find, so we give it these what do you say, these 10 clusters, which I call ideas in my program. So we give it these 10 ideas, and we say, okay, for each of these ideas, give me a top quote, and then finally tell me the top 2 quotes from these top 10 quotes. And then we do this iteratively for each of those 20 chapters. So at the end, we do this kind of summarization, iterative summarization, until we are left with like the top 10 quotes in the book, and that kind of traverses the entire book within itself. The other thing that you could do if you're looking for the inherent structure could be, instead of doing a chapter-wise clustering, you could do a book-wise clustering, because and instead of maybe encoding at the paragraph level, you can encode at maybe you can cluster at you can see a chunk of 5 paragraphs and convert that into a vector, right? And then find let's say the top 20 clusters in the entire book. Maybe that's the top 20 ideas that James Clear wants to convey in his book, and you kind of retrieve that.
Yeah, it's a beautiful idea. So many things to explore there. Yeah, so just the naive approach then is do some kind of hierarchical clustering, and then you produce this tree structure of embeddings. And what you can do is you can take projections of information at different levels of depth. So you can start off at the top level. You can create an interactive process. So that means you can say, here's some information. You can even automatically generate some questions, because there's a dichotomy between search and discovery, and you want to lean more into discovery. So you're almost prompting the user to, like, well, you could ask this question, you could ask this question. They could traverse the structure almost without having to think themselves. But I also like this idea. I don't know whether you've seen this paper out recently about creating a social ecosystem using agents and language models. That was out yesterday. Because the thing is, at the moment, the way we're talking about creating this structure is quite fixed. But what you could do is you could create an ecosystem of different personalities. So that might be the Noam Chomsky personality, there might be the AI skeptic personality, and you can get them to kind of like query your system dynamically, and then you get this like emergent structure, right, which could be presented in different ways. So there are many ways of remixing and emerging the structure of that book to help people dive into it from their perspective.
Yeah,
that's an interesting idea.
That's very cool. I actually read a paper about some RPG game where they actually create the characters in the game just by prompting the behavior, like the kind of personality. And with all these behaviors that you prompt, you can always link it back to vector embeddings, because they can still draw from a common database of memories. And then with all these relevant memories taken for their particular personalities, I'm pretty sure they can interact in the right manner. It's very cool because GPT allows for this with just prompting. That is amazing. You don't even need to pre-train it, or you don't need to have to do further fine-tuning. You can just prompt it. Yeah, this brings up a lot of potential. Yeah, and I really like what y'all been talking about, hierarchical clustering. You can cluster the embeddings not just at the paragraph level, but at the book level, and you can use some form of iterative prompting to go from top level to middle level, like the 2 quotes for each chapter, and then you can use this middle level and generate a final output. So there's a lot of possibilities we can do here. Yeah.
Yes. The only elephant in the room is copyright. But maybe we'll leave that for another. Yeah, probably don't want to talk about that.
Yeah,
Sure.
maybe we open the floor for some other questions. We do have about 15 minutes or so. So y'all have anything to ask? Like maybe you can ask Manas, like, how much money is he making, that kind of thing. Yeah, that kind of stuff. Yeah.
Not much, not much.
If not, actually, I have a question. And the question I have is, if we were to run the query right now on your sites, how is because you are running using ChatGPT, but your site doesn't require an API key. So are you bearing the cost whenever we search it on your site?
Yeah, actually this lab that I'm a part of, they have some grants for like student-based projects. So we've just asked for around $20, I think, in grants. So yeah, but the reason why we're doing this for free right now is because 1 million tokens cost just $2. So it's fairly cheap. And to be very honest, the traffic on our site is around 2,000 to 3,000 views over the last 3 weeks. So it's not like 1 million people are coming to our site and querying the book. When that happens, then we'll have to figure out a much better strategy. But for now, this naive approach, I think, seems reasonable, because it's just at the end of the day, if the purpose of the project was not, again, it's a project, not a product, right? So the idea was, okay, how fast can you build it? What do people think about it? And basically to just explore the idea of vector embeddings and seeing what's possible with that, and then extend the knowledge that you've gained over here into something more complex, like an actual agent AI. So yeah.
Cool. Yeah, because I played around with your site. It's quite exciting. Have you tried whether it's possible to encode out various modalities? Like, for example, right now the embeddings are more for text, but what if the book has stuff like images? Like, how would you want to, if you were to do an extension to the project, or I don't know if it's possible right now, like, how would you display the right images as well when people want to find, like, atomic habits? If I want to find out what's the most effective habit, then maybe there's a diagram in the book. Like, how do you think it's possible to be done? Yeah.
Okay, that's an interesting question. I mean, to be honest, I haven't thought of that. But maybe an approach could be, let's say it retrieves a paragraph that's very, like you measure the distance of that paragraph from the image. That's again a very naive approach. You just return that image and say, okay, this image should be related to the user's question. But maybe a better approach would be you use some sort of, I'm pretty sure that there are some visual transformers where you can embed even the image data. And if you have it in the same dimension of the query vector, you can kind of do a cosine similarity there as well. So you kind of return the most relevant image with respect to the query vector. But yeah, maybe I would consider something like that. But I'll have to read up more. I'm not too informed about that.
Yeah, I mean, I have a solution. There's this image question answering API where you can ask a question to the image, or you can put an image and out comes the text description that's used in Visual ChatGPT. So with that API, you can encode all the images as text. Okay, so there's a big problem with images right now is that the pixel domain is actually not the best way to interpret the picture. There's too much information in the pixels. But if you ask ChatGPT to or ask the API to give it in the form of text, if your images can be interpreted as text, I'm very sure you can generate an embedding for that text that represents the image. Then you can do the vector lookup table for the image separately.
Right.
Yeah.
Sure. I think that's a good idea. Like kind of describe the image and then do the same process that you would do for a paragraph. Yeah, definitely.
Yeah, I'm sure we can do that for voice as well. Yeah, so Sam Altman from OpenAI, he said everything can be represented as text. And I'm starting to see it more and more now. Like if you can encode it into the text domain, GPT can handle it.
Well, yeah, that goes to philosophy very quickly. But I'm really interested in this idea. I love the idea of remixing content and also making it educational. I already use a reader app and I use summarization quite a lot. And I could say, because there are apps like Blinkist that take books and they compress it into like 10 minutes. So you can do this automatically. I can say, it's almost like I want to structure my learning. Give me the 10-minute version of this book, do TTS so I can hear it like an audio, right? And then And then we can have this structured reiteration, you know, where it almost says, okay, well, there are these things you might want to ask further questions on. So now I'm going to remix that. And you're creating this iterative learning process, but you're also time boxing exactly how much time you're willing to invest in the material.
True, and I think the interesting thing with what you just said is it's entirely personalized. Like you're branching off, what questions you would ask and what nodes you want to explore would be entirely different from maybe the points I want to explore further. And maybe the other interesting thing could be, there's some point that the author talks about in Atomic Habits, but that's actually related to some other idea in this other book that you've embedded. So you can kind of relate ideas across books, and I mean it could be an interesting, interplay of embeddings.
Yeah.
Hi, everyone.
On that, so the amazing thing is that information has a shape, it has a structure, and like John was just talking about, there's the subjective experience, right? So every time I go to Paris, I have an omelette in Paris. I know what I felt like when I had the omelette in Paris, but the thing is, information is presented by the author in a way that they understand because it's hanging off all of these experiences and things that they know. So you're now remixing the information to hang off experiences and things that you know. So that's an entirely new paradigm of personalized knowledge transfer.
So,
yeah, anyway, hi, everyone. Hi, John.
Hi.
Yeah, who else is here? Hi, I guess, Manas, you're talking today.
He just presented
Tim and Dylan.
Habits.
Yeah, so apologies if I missed the discussion before, but can I just pipe in on something you said, Tim, and I guess that you guys have been talking about, which is that somehow that there's some value in summarizing information. And I think that does make sense, but I think I would move a little bit cautious. I'd be a little bit cautious because there's in summarizing, you're actually losing a lot of maybe second and third order effects. Yeah. So, for example, I don't know, you have these a summary of books that have existed for a long time, right? And yet somehow they have not replaced the actual books. So I think that there's something to be said for in the way, for example, that an author presents something. So for example, if you took Isaac Asimov, I think all of you know Isaac Asimov, you could summarize it, but somehow there's a big difference in reading a summary of Isaac Asimov versus reading Isaac Asimov, right? I mean, what do you guys think about that?
Yeah, no, I mean, so this is the fundamental philosophical debate about AIR and, syntax and semantics and subjective information. So when an artist creates something, it's not just the aesthetics, it's not just the brushstrokes, it's the intention, it's the subjective experience, it's the pragmatics, do you know what I mean? It's all of that context. But the thing is, there's a spectrum of information. There's the ontologically subjective and there's the objective frame of information. So in a sense, when I get GPT to summarize something for me, what it does is it completely distills all of the objective information and it makes it easier for me to understand, but I cut off all of that subjective contextual information. So there's actually a kind of interesting trade-off between those two.
Yeah, exactly. Yeah. And it might be the case if, let's say you were talking about like bounded time. I definitely agree. If you have a bounded time, you want to, let's say, give to something. Yeah. Like maybe a quick summary is the way to go, right? Like if I can't afford to read all of iRobot, if I want to, for example, build on that and I'm attending a talk talking about Isaac Asimov's work. So maybe if I could get a quick summary to allow me to appreciate the talk, that might make sense. Absolutely.
Just one other thing to throw in as well. So when I read books on philosophy, especially if they're written by David, well, I better not say this because you're publishing this, but there's a kind of circumlocution, there's this torturous repetition, like lots of variations of the same thing and the same thing. And in order to learn something, you need to be familiar with it, you need to think about it. So when you're sat there on the train, reading the same thing again and again and again and again, you're internalizing the information through familiarity. And actually, when you represent information like we are, it's the best way to learn something because you're kind of representing it. But there is something about the pedagogical experience, which is just sitting there with a book and kind of like entangling that learning experience with the situation you're in. It helps you remember it. It helps you because those subjective links actually tie into the information you're learning. So if you objectify something too much and you distill it too much, it might make it harder to learn the information.
Yeah, exactly. That's precisely what I'm thinking as well. And so, yeah, one of the things I've been thinking deeply about is how can you balance these two? I mean, I want to inspire people to learn fast, but then I also want to inspire them to read things on their own that are not distilled, right? You want to balance these two. And my hope is that moving forward, this balance is emphasized, and we don't just move to quick and dirty, that we still, because there's something to be said for struggle, right? Like if you struggle to read something and you hack your way through confusion, actually you develop a completely different point of view than if somebody just explains to you what is meant here. Yeah, so
Actually,
I think balance is important.
There's a solution for this balance. Like when you give a summary or the ChatGPT gives an example output or the output based on the prompt like this, you can actually augment the output with some link to the book, like some pages, link to the pages. I think Mana's app does that as well. So you actually link to the actual page, then you can actually read the page that you are interested in. Because moving on in this digital world, we are just going to be overwhelmed by information. So having someone or something to, in this case, vector embeddings, to try to filter the information that is relevant for you would be a great help, because you will save a lot of time than flipping through every single page yourself. So maybe that is the middle ground.
Yeah, that's interesting, maybe. So Manas, this app you wrote is open right now?
It is. Actually, the link is on the screen. I'll just put it in the chat. Maybe
yeah, I see it now. And
try.
are you just, I mean, I know, I apologize, I missed the beginning. You probably explained this, but can you give me like a 1 minute? Like are you using the OpenAI API and basically it's interacting with ChatGPT?
Sure. So I'll maybe just distill it down. So what we're doing is we've embedded every single paragraph of the book, and we store that in a database. And when somebody comes to our website and asks the website a question, like in this example, how to stop procrastinating or quitting smoking, or any practical question, that question is also converted into a vector embedding. And then we do a cosine similarity between the query vector and all the embeddings of the paragraphs. And we return the top 5 paragraphs that it finds that's relevant to your question. We give that as a context to ChatGPT along with the question. And then we say, okay, answer this question in the context of this stuff from the book. And then alongside that, we also display those top 5 paragraphs actually quoted from the book. So the user can not only read the summarized answer, but they can also swipe through the paragraphs and see if they find more relevant information.
So is this
by the author's voice.
Is this for a specific book, or can I ask a general question and it will look at multiple books?
Right now, this is only for one book, but we're planning to have this kind of global search across the books, because we basically automated the task of adding a book. So adding a book is now just, okay, getting the PDF and putting that in there.
Great. Okay, thanks. Yeah, so I let you guys continue where this discussion was going.
Okay, I think this is actually a great time to go to the theory, because we only have about an hour left. So I would like to thank Manas again for showcasing this app. I do encourage everyone to go try it out. It is really cool. In fact, this kind of vector embeddings and this kind of memory augmented retrieval will be the future. Okay, in fact, it was actually the past. It's just that with GPT, it is definitely going to be the future. And even stuff like Bing search probably also use vector embeddings at the base, because I was actually playing around with it. It actually generates quite reliable responses and can potentially help to solve the hallucination problem of large language models. Okay, so without further ado, okay, if you have any questions, feel free to put in the chat so that we can talk about them towards the end. If not, let's go through the magic behind vector embeddings and how it's developed. So firstly, this is the slide on embedding space. So this is actually for word embeddings. It's just a hypothetical slide where you have different animals like cat, dog, houses. What is actually an embedding? So an embedding is, instead of giving it in the word space or token space, we want to give it in a vector space where each of these vectors here, over here is a 7-dimension vector. Each of these dimensions should encode something, like some attribute. I mean, we probably don't know what this attribute is, but it could be like living being. Like over here, cat, kitten, and dogs are living, so they are towards the higher side, and houses are not living, so they are towards the lower side. So you can do that for different dimensions, different categories. You probably cannot define these categories because these embeddings are actually learned through backpropagation. if you handcraft them, you can probably give these embeddings. Okay, but so far, most of the embeddings I heard are all learned by backpropagation or some other method, okay, which is not handcrafted. So you probably cannot determine which of this kind of dimensions correspond to what kind of attributes. But if we were to do some form of like dimensionality reduction, what we expect to see is like cat and kitten, very, very similar. So they are clustered together in the embedding space. Dog is similar to cat, so it's very near as well. And then like houses is the furthest away from all of them. So their distance is very, very high as well. So if we were to do stuff like with this embedding vectors, what we can see is that, okay, if we start from the origin as the center, you can see similar vectors, all right, have very, very similar directions. Like over here, cat and kitten. Over here, it's almost the same. While vectors that represent different things have very different or diverging directions. So take that in mind, because later when we talk about cosine similarity, this will be used to identify like which vectors are nearer each other and which vectors are further each other in terms of the semantic space. All right, so this is of course assuming that this gives us semantic meaning. And for the book club that Mana showed just now, it is quite amazing because actually I tried it out myself as well. I also tried out other ways of doing OpenAI embeddings and doing my own documents. It works surprisingly well. So there must be something that the OpenAI embeddings have done correctly. Okay. So again, let me just emphasize this is for words. Okay. How can we extrapolate it? How can we do it for paragraphs or sentences? All right. So that's something interesting to think about. Okay, before I move on, this diagram at the bottom just shows that, you know, if the word embedding is correct, from like man to woman and king to queen, like from male to female, you should get the same direction. So you can see in this vector space, direction is very important. Okay, so let's move on. Before I move on, can y'all see the slides? I know it's a bit late to ask, but you're able to see the slides, right?
Yep.
Okay, let's move on. So traditionally, like how do we get semantic similarity if we don't use vector spaces? So this is a very, very traditional method. I don't know how many of you have heard it. TF-IDF, who has heard it before? Anyone? Okay, Zuri has heard it before. Okay, probably the rest, you should have seen it somewhere. This was used like long time ago to try to find out like which of the terms are more relevant to a document. So like, for example, if I search the word like GPT, okay, let's say the word GPT, I can then check through all my documents, okay? Like we can find the term frequency for all the documents. Like for example, if the first document mentions the word GPT 10 times, the second document mentions it 1 time, and the third document mentions it 0 times. Okay, probably what you want to do is you want to give a higher weighting to the first document, all right? Because the first document is more or less the one, so term frequency is the term frequency of that term divided by the total terms in the document. So this is like how often it's mentioned. Okay, this IDF is just to say that, okay, if the word is too common, all right, it's also appearing in all other like documents, okay, then we weigh less. So this is just a form of like regularization term, so that words like very common words like the, of, is, you know, that kind of thing won't kind of influence your search too much because it appears in a lot of documents. So combined together, this TF-IDF is a very rudimentary way. You just multiply the TF by IDF, okay, and this will give you more or less like the score of each document, how relevant it is to your search term. Then you can also do it across search terms. You can just multiply the TF-IDF across all the terms. So this is the traditional approach, and there's a few issues with this approach. Okay, the first issue is, of course, if we only go by word counts, you must have the exact match. It means that you don't take into account like similar words. Like for example, the word like happy can also mean like exuberance or elated, you know. But if you were to do by term count, you might miss them out unless you go to the root word. Okay, I mean, there have been cases of people trying to overcome this issue, but it's still a very difficult issue to solve, right? So how about word order? Okay, you know, the back of words approach that we talked about, like we not in this venue, but like has been talked about in NLP spaces like a few years back before the rise of LLMs. Okay, they actually use bag of words to determine like how to filter spam mails, stuff like that. It's not too far away. One of the issues with this kind of bag of words approach, like TF-IDF, is that the word order is not taken into account. Like, for example, like A eats B and B eats A, it's kind of different in meaning. But this kind of TF-IDF approach would not be able to find that. And another bad thing is that you need to probably calculate the term counts across all documents, which means every time you want to get the term, you need to count. So this is not ideal. Okay, so what has been done is once we have introduced this vector embedding spaces, we are able to store the meaning of each vector, of each paragraph or each sentence into a vector space. It's the same vector space you saw earlier here, just that it's for paragraphs and for sentences or for books. But how exactly is this done? Or how is this magic done? Okay, let's try to decipher it. Okay, so this is from the OpenAI website, and you can see this is, this is what the vector-based lookup for sentences, paragraphs can do. It can do search, okay, basically by like cosine similarity. Later I'll talk about how to find the similar vectors. You can find out which are the documents that are more relevant to your query string. So this search is exactly what is powering Manas, the GPT book club. All right, you find what kind of quotes is more similar to the query and you return those quotes. Is that correct, Manas? That's correct, right? This.
Yep.
Okay, so this is the main thing that we have seen just now through the Atomic Habits GPT. Right? There's also other use cases like clustering, recommendation, anomaly detection, diversity measurement, classification. Yeah, so all this uses vectors. And you can see that this vector is a really, really powerful approach to model semantic meaning. And actually, it's also related to memory. I believe memory is stored in a vector form. Also, we have an origin and a kind of movement. Of course, we can talk more about that when I talk about memory next time. All right. So I feel vectors have the right structure to represent a lot of the world's data. So let's move on to how are the embeddings created. So any of y'all have seen this diagram before? Or maybe I should ask who has
transformers.
Yeah, that's the transformer. All right. So everything that you see in this vector embedding today are transformer models. All right. I'm sure this is a very familiar thing to you by now. Audrey Kapati has this video of how to code transformers. Cool video. Check it out. Yeah. So the thing to take note is that when we actually have the embeddings of the tokens, so like a sentence like that, I am a student. Okay, or Jess, she's a student. This might be given to tokens. So the token can be like token number 30, token number 104, token number, I don't know, 20,000, 10,002. All these embeddings will then be looked up by an embedding table. So you have your index over here, like your index 30, and then you get your embeddings over here. So your embeddings is this n-dimensional vector. Typically, we use 1024 dimensions for transformers. So 1024 dimensions. And then you can read off this 1024 dimensions and put them inside this embedding layer here. So this is what is done for transformers at the beginning. When you first group by tokens, of course, getting the tokens is important. Like you use byte pair encoding, like frequency-based ways to generate tokens that have the most likely, the most informative for your use case. Like for example, the word like houses always appear with the S, we will chunk the house and the S together in one token. Okay, so this is just one example of how the embeddings is initially generated in a transformer model. Is at the input layer, you do an embedding lookup table and you get the embedding here, which will then be processed through self-attention and so on to refine the embedding space. Right? I will not go through in detail because this is not a transformer kind of video. I would like to just focus on this embedding over here. This embedding is learnable by backpropagation. Okay, while y'all might not think it, but output probabilities can actually backpropagate all the way to the front here, and then it can modify this table here. Okay, so of course you can also use fixed embeddings, but these token embeddings are learnable by backprop. And so the diagram that you saw earlier of the cat, kittens, and all this comes from the input layer embeddings, like how is a cat structured, how is a kitten structured, and At the initial layer, is all learnable from the backpropagation, from the objective of predicting the next token. It's quite cool. Just predicting the next token can give you semantic meaning at the initial layer. So now that we have settled this for individual like tokens, how can we get this for paragraphs? So this is like one of the, before we go through the detail, I'll just show you this results that OpenAI gave for DBpedia. It is structured information from the Wikipedia website. And over here, they applied the embeddings across different categories, like album, animal, artists. Yeah, so you can see like the green color ones appear together, the blue color ones appear together. They use PCA to get principal component analysis to reduce the dimensions from 1536 to 3 dimensions. And then we can visualize like the embedding space and how similar it is to the category. So it is really quite similar. Like I've tried out the OpenAI embeddings. It works generally quite well for most use cases. You can see that in this DBpedia result alone, you can see the category is actually quite well clustered already. Yeah, so if we have the right clusters of like, so this is all done like using like some form of unsupervised learning, because like we don't have the ground truth. We are just like performing the embeddings, and it can already split into distinct clusters, which is quite amazing. All right, so if you have done like clustering before, this is not an easy problem, because to find out clusters, you need to know what kind of meaning to group by. And the embedding space already can sort of cluster into different clusters, which is actually pretty amazing. Okay, just pause here for a while. Any quick questions so far on what I've covered, like this previous slide or this slide? Okay, if not, I'll move on. So this is the secret sauce, okay, of OpenAI embeddings. Take a look at this paper over here. This paper is called Text and Code Embeddings by Contrastive Pre-Training. And this tells about how they train it. Okay, the key idea is that they use the input using contrastive learning. So X and Y can come from the same kind of paragraph, or they can come from different paragraphs. And then if it's the same paragraph, we expect the cosine similarity to be, anyone? Same means 1. Okay, different is -1. So if they come from the same paragraph, if you have paragraph 1, or maybe you have paragraph 1 part 1 and paragraph 1 part 2, you expect this to be similar to each other compared to like paragraph 5 for part 1 and paragraph 4 part 2. So you expect the first two here, this part 1 and part 2, to be more similar to each other, and this part 1 and part 2 here to be similar to each other, compared to like from this paragraph 1 to paragraph 4. If they're not talking about the same stuff, you expect it to be dissimilar. So they train X and Y by contrastive learning. Basically, they take X and Y either from the same paragraph, and then they make the cosine similarity at the end of the embedding space vector, this Vx and Vy, and they make it to be, the loss function will force this two to be same, like output of 1. If they are from different paragraphs, the cosine similarity function, the loss function would force the cosine similarity function to be different. So in that sense, through contrastive learning, we actually make the embedding spaces go further and further away if they are of a different kind of input. All right. So yeah, any questions for this contrastive learning part?
How does this learn the semantics?
Okay, this is a good question. So the semantics part, it doesn't exactly, it's not really defined over here, but because when you take in like stuff from the same paragraph, you expect these two to be semantically similar. It's just the way that they take the data from. So by grouping the data, like X and Y come from same paragraph, or like same part of the like input space, we are like sort of giving it some form of human guided semantics. Like we tell it, okay, these two are similar, but the other two from different paragraphs, they are dissimilar. So,
John, can I ask a question? What if in the same paragraph, you're actually trying to make a point about differences? like then part one of paragraph one and part two of paragraph two actually might not be similar, because you're actually trying to make a point, right, about two things that are very different. How would that how do you reconcile that in this context?
Yeah, so you have to split the paragraphs smartly. So in this case, I read through the paper, they did not exactly say how they did it, but I'm pretty sure that when they split it, they probably did for, okay, so whatever you said would definitely be a problem. So
Okay, yeah, that makes it. Yeah, I mean, obviously for many of the things, this would work perfectly, right? Yeah.
right, so we just hope that in the grand scheme of things in the same paragraph talks about the same stuff. If not, you're gonna learn the wrong things.
Yeah.
So as to answer Zeri's question as well, this contrastive learning, it doesn't actually encode the semantics as per next token prediction, because you don't really need to generate the next token, you see. All you're doing is to make sure that your embedding space differs if your input is from a different source or different area. So I feel like the embedding space here is not as strong as the embedding space for like next token prediction. Okay, but OpenAI use this. There must be some reason. Okay, I'm still not able to figure out the reason actually, because I still think next token prediction kind of.
So it also didn't make use of word level embedding, right?
Yeah, so what I suspect is like this. These are already pre-trained from the next token prediction embeddings, and they are just like sort of a fine-tuning step. Okay, so this is my own guess, okay, because they didn't really say like how this is done compared to the from the supervised learning step or the so what I suspect is you already have a word, like this is the initial word embeddings, embedding 1 for class 1 and like embedding 2, like let's say these are the 2 points in the thing. Okay, my drawing is quite bad, but but if let's say these are supposed to be different, okay, we sort of through the contrastive learning function, we split their embedding space, or we basically shift the embedding space for these two supposedly different embeddings further and further apart using contrastive learning. So there's a lot of work done on contrastive learning. You can search this thing called Siamese networks, and it's essentially this concept. So eventually, if you do the contrastive learning enough on enough data points, what will happen is the data points that will be grouped together will be all of the same class, like all of the circle class, all within like a certain radius in the 2D space. And then all of like another class will be outside this radius. Yeah, so this is eventually what we hope to get out of contrastive learning. We hope to push together the similar kind of embeddings into the same radius, and the embeddings that are further away, embeddings that are different, we try to push them to a different region. Yeah, so that's more or less what contrastive learning is doing.
So I'm curious, like when they embed, are you embedding the entire paragraph?
Okay, so this, maybe I'll show you the diagram. It's easier that way.
Okay.
So it's not in the paper, but this is exactly what, oh, sorry, let's go back. This is what is done. So like, for example, this is the input paragraph. What they do is they just go through the entire network, and just at the final embedding before the output, this will be the paragraph embedding.
So they're embedding the paragraph, not necessarily like the words in the paragraph.
Yeah, so the paragraph embedding will be based on like after you embed the entire paragraph, which also means that your context length here matters, because you can only embed as much as your context length can. As you know, the causal self-attention, this kind of attention only works with the tokens behind. Like, for example, this hat can attend to all the tokens before it, because you can only attend to tokens behind you, not in front of you. So if we were to look at the embedding space for the final word or final token here, and we take the final embedding here, this should give you enough information to predict the next token. And so this is the embedding that we use in the OpenAI embeddings. Okay, is that clear? So I put this diagram specially. It's not in the paper. I thought they should do a diagram like this, but this is the kind of embedding space that they are taking. The pre-output layer, final token, that's the embedding for the entire series of tokens.
And the idea is that has somehow, because of all the mixing, there's token mixing happening here. Because of that, it captures the entire paragraph.
Yes, that is the, so it's not explained like that in the paper. The paper was not very clearly written, but this is my intuition behind why it works.
And then so does this also capture, for example, levels of similarity and dissimilarity? Right. So like you could have two paragraphs be somewhat dissimilar, very dissimilar. Like, so this will capture that in the distance between the paragraph embeddings.
Yeah, so my own personal opinion is contrastive learning is not required. You can just use next token prediction and just take this embedding.
Yeah.
You can just learn the initial embedding space, run through the transformer to get the final embedding, and that's the embedding you can use for your embedding of the entire chunk. So this is my opinion. Okay, why did OpenAI not do that? I'm not sure. Yeah. So maybe this is not explicit enough to split the embeddings according to the context. Maybe it's not explicit enough. Yeah, so they use contrastive learning to do it. Yeah.
Wait, sorry, what do you mean by this is a replacement to using contrastive learning?
Okay, so this next token prediction is what is done in transformers already. So what we can just do is we can just extract out this particular embedding space for the entire chunk. So you don't really need contrastive learning for that. You can just do supervised pre-training, which is self-supervised training, where you just keep predicting the next token. Like the cat is out of then you just predict the next token back or something like that. Yeah, so you keep doing that. Initially, what will happen is your embedding layer here will be learned by back propagation, because you want to maximize the next token prediction, which is maximize this objective prediction of next token, okay, given all previous tokens. So this is the kind of probability that we are maximizing, and most commonly we use a log, okay, for the kind of, so if we do this, this is like the maximum likelihood objective, which will lead to you back propagating through the network, and eventually your embedding layer at the front would also be updated accordingly. So my intuition is that you can just use this and then update this embedding layer, run through the model, and then you get this particular embedding here, and that can be your paragraph or sentence embedding. Yeah, did that make sense?
No, but that doesn't account for any semantic like contrast between the paragraphs. Like, it's just a arbitrary embedding you're getting for next token prediction. I don't see how that's similar to like, okay, one maybe you can say it's implicit, then how is it similar to using explicit methods like contrastive loss?
Yeah, so what I suspect is that this may not be sufficient for like paragraph level. Maybe because the objective is just next token, the objective is not inter-paragraph. So that may be why OpenAI use a contrastive learning method rather than this next token prediction method to learn the OpenAI embeddings. Yeah, I think this is a good discussion, because I start to see why perhaps this embedding may not be that great a representation, because the objective is just next token, while what we are interested in is actually next paragraph or next sentence kind of prediction. Yeah, so maybe that's why they use contrastive learning, because you can't really do next sentence or next paragraph prediction. It's just too many tokens to predict. But you can use contrastive learning to tell the machine or tell the model, okay, these two sentences are similar, or these two sentences are not similar. Yeah. So
the embedding layer is what the contrastive loss they learn, is it?
This embedding layer over here is this square here. It's the same. It's just that instead of going through the next token prediction, this is the contrastive learning. We just take this penultimate layer, and then we just use the embedding space of the penultimate, or basically the layer before the softmax to output. All right, we just take that and then we just do contrastive loss on it. Yeah, so that's exactly how they train it. They don't do the next token prediction. They just do contrastive loss to push away and pull together like different or similar kind of embeddings. Yeah, is that clear?
Apologies, go back to the previous slide you were showing.
You mean the slide with this one?
Yeah.
Okay,
so
yeah.
It's the penultimate layer that they're doing the contrastive loss, is it?
Yeah, this layer, this one, right before the final token output. Here, and it's specifically only for this. last token.
So what you're inputting is the entire chunk of tokens in that particular paragraph, but split into
Yes.
two.
Yes, and then all you are taking out is just this embedding layer here, which by right, because of the self-attention, already pays attention to all the tokens in front and gives you like the consolidated embedding of the entire sentence. Yeah, just to highlight, the model does not include this encoder part. Okay, this encoder part is the original one, but for GPT related models, there's only decoder only, which is just this part here. Okay, is anything else that you are not clear of?
Yeah, just clarify one bit. So your question here is why not just take the final embedding of the last token? What do you mean by that? That's what they do,
Okay.
isn't it?
So my thoughts is, why don't you just do next token prediction as the loss function, which is the probability of next token, you make it as high as possible to the actual token. Why not you just do this? You learn the initial embedding layer, and then use this initial embedding layer, you can get the final embedding layer without doing contrastive loss. So that was what I was thinking. Why not just do away with contrastive loss? Yeah, but after discussing with you, I realized why they might have needed to do it, because this is for next token prediction. It may not work very well for sentence kind of similarity, because the objective function is different. Here, the objective function is to maximize next token prediction, basically minimize the error for next token. Here, this contrastive loss, the objective function is that we want to make this vector similar to this vector if the inputs are the same. So this is exactly the sentence level kind of loss.
I see. Yeah, thanks for clarifying.
Yeah, so that may be why they use the contrastive learning here, because it is very hard to denote or to basically to do a kind of sentence level like self-supervised loss. You just cannot self-supervise on all the tokens of the next sentence. So yeah, that might be one of the reasons why. Okay, let's move on. Yeah, of course, this is again subject to the how well you split your data. So if you from the two input from the same paragraph, you need to make sure that they are semantically similar. If not, if like Prof. Mehul said, if this two parts of the paragraph talk about different things, then this contrastive learning loss might not be the right one. Okay, so I just want to show you this part on finding the manifold. So this is Yann LeCun's slides. Basically, this is like, for example, you can treat this axis as your input X maybe, and like this axis here can be the like embedding space. All right, and what you want to do is like for this input and the current embedding space, you want to basically have, okay, so maybe not input, embedding 1 and embedding 2. Okay, we want to train it such that if the embedding is of a similar nature, they all form in the same manifold here. They all fall in this manifold, which means that if you were to view it as a loss function like that, or valley, okay, these are your similar information. So similar information, maybe they all fall at the valley of maybe -1 and the, okay, so in this case, this is valley, but if you think about it in cosine similarity, this part at the bottom should be actually 1. Like similar vectors should give you a cosine similarity of 1. These similar vectors give you a cosine similarity of -1. So if we were to form the right manifold, eventually what will happen is you will be able to just from the two embedding space alone, you can tell whether or not is it similar or dissimilar. Like this E1 and E2, okay, falls within the manifold, which means that they are similar. And this E3 and E4 falls outside of the manifold, which means they are dissimilar. So we seek to find this kind of loss surface such that the similar embeddings would be together in the manifold, and the dissimilar embeddings will be outside of the manifold. And this manifold is this U-shaped thing here. Okay, however, there's
Did Yann LeCun define manifold like that? Because correct me if I'm wrong, but traditionally, from what I understand from manifold is, let's say you're given a subset of your data, right? That's manifold is defined as the point in which that the plane in which that the points fall onto. So that's actually what you're seeing represented from across all your data points.
right.
So traditionally, what people view the manifold is you just want, like for example, you think about it in terms of a kernel function. So you 2 points those similar points should lie closer together in the manifold compared to, let's say, dissimilar points. So dissimilar points, let's say, at one end of the U curve you're showing, and a dissimilar point is at the other end of the U curve, very far away, in terms of local smoothness. So it shouldn't be outside of the manifold, right?
Yeah, in this case, the manifold actually represents like the way to form the data together, like to represent the data such that you can like abstract from a higher dimension to a lower dimension, which is this U shape here. Okay, over here, what I'm using his diagram for, okay, is just to showcase like if let's say the manifold here represents all the vector embeddings that are similar to each other, all right, they should all fall on the same kind of plane. And what we really want to learn is we want to learn the valley. Like over here, if you see the animation, this part here is actually high. I use a different color. Like you can see that this part here is actually of a higher height than the one at the center. So eventually what you will want to do is you will want to find the loss function surface such that the loss function is the lowest at where your manifold is, which is this part here. And I define this manifold for this context of embedding space to be embeddings that are similar to each other, to be on that manifold. Okay, so anyway, we don't really need to use like this manifold theory. The idea I want to point out is this part here actually. Contrastive methods, in order to find out this low energy region, which is the region where all like maybe the similar embeddings are. Okay, these data points can be the similar embeddings, while this part here can be the dissimilar embeddings, like this other dots here. So if we were to use contrastive methods, okay, how do we do contrastive methods? Okay, so this is a bit of a background. Contrastive methods, you need to take any sample compared to another sample. So if let's say these two samples are different, okay, I push away their embedding space, right? If the two samples are similar, like for example, this purple sample and this one here, if they are similar, I want to make them in the same embedding space. So the same embedding space can be characterized by this low energy region here. If you fall within the low energy region, okay, then what will happen is that it means the samples are similar to each other. In this case, the embeddings are similar to each other. Okay, but anyone can tell me what's the problem of contrastive methods? Like, how can contrastive methods fail? Anyone want to try? I mean, the idea sounds right. The similar embeddings will go together, different embeddings will be further apart. But how can contrastive methods fail? Dylan, you should know.
It's based on the choice of your pairing.
Correct. So if you have a lot of input samples, you kind of need to do pairing. So let's say you have n input samples, you kind of need to do n choose 2 pairings, right? So if you have a lot of samples, you might pair a lot, but that's not the main reason. The main reason actually is the dimensions. So if we have 2 dimensions, like 2D, all right, I mean, finding the plane might be quite simple because you just need to find out stuff along this line. But if you have a 3D diagram, all right, you kind of, let's say your manifold is this plate over here. You kind of need to take samples along this 2D plate, which can be quite a large area. And you also need to take contrastive samples outside of the 2D plate. I mean, you should use a different color, like this green color. You also need to take contrastive samples outside of this 2D plate, which means that the more dimensions you have, the more samples you need to kind of distinguish where the plate should be compared to where the plate should not be. So we call this plate actually a plane, a hyperplane. So we need to kind of distinguish where the hyperplane should be compared to where the hyperplane should not be. And this is actually very, I would say it scales exponentially with your dimensions. Like as your dimensions go higher, you will need more and more contrastive samples in order to get the right kind of manifold or hyperplane. Okay, so this is one of the problems with contrastive learning, and Yan LeCun himself said that contrastive learning won't scale, and I kind of agree with him. So he proposed like regularized methods. So I just wonder whether we could do some form of regularized method to kind of learn the embedding space for this case in OpenAI embeddings. I mean, this is something to look into because I'm quite sure the OpenAI embedding space of using contrastive methods doesn't work for all cases, okay? It just works well because their data set is huge. So it works well for most use cases. But just learning this contrastive loss may not be the best way to go about it. Okay, we can talk more about it later. Let me just finish the rest of the slide. Okay, so the next thing I'm going to talk about is how to measure embedding similarity. So we all know that embeddings can be measured as a vector, all right? And vectors, there are a few ways to do it. So one of the more common ways is this thing called L2 distance. L2 distance basically measures the distance between the two vectors. Like, for example, if the vectors is in a 2D point, the L2 distance will just be like Pythagoras theorem. You take the first one, like you take this squared, okay, and then you take this one squared. So it's just the difference in the x and the y axis. So if there's more x's, you can take x squared plus y squared plus z squared and so on. So you just take the sum of the differences in each dimension, and that's the L2 distance. The closer the L2 distance, okay, in the 2D space, you can search, it's called Euclidean distance. Okay, the closer the Euclidean distance or the L2 distance, the more similar the vector is. So that is all right to use. Okay, the problem with this kind of L2 distance is that as your number of dimensions increase, all right, this L2 distance becomes less and less informative because there will be a lot of dimensions whereby the difference squared can go to like very, very close to infinity. And this will mean that all the L2 distances will be very high. Yeah, so L2 distance does not scale well with dimensionality. And that is the reason why most people now prefer cosine similarity. So instead of doing like distance between 2 points, which doesn't hold well for higher dimensions, cosine similarity actually does hold quite well for high dimensions. Okay, because what you need to do, okay, firstly, the compute is not much compared to L2 distance. The compute is just a dot product and some magnitude. Firstly, all you need to do is just measure like the angle. Okay, so if we were to go back to the earlier diagram on the embedding space, if the two vectors point to the similar direction, it means that they are likely representing the same thing. So we use this idea here to do cosine similarity. When we get this theta here, like two vectors very, very close to each other, the cosine similarity here, the cosine theta will be very close to 1. And if we were to look at the cosine graph, it looks like this. So this is the cosine theta. All right. And this is theta. Okay, so if we start with 0, okay, cosine 0 is 1. Okay, I'm sure you all have studied trigonometry before. So this cosine 0, and then we can see at the back over here. So this point here, okay, this point here is actually pi. Okay, I mean, if you do in radians, it's like pi over 2, actually, pi over 2. And this point here is pi. So you can see that the cosine similarity is highest when the vectors are very close to pi, which is 180 degrees. Pi radians. Okay, this is in radians, right? So if we were to look at this diagram here, cosine similarity actually tells us which vectors are similar and which vectors are dissimilar. Similar vectors, so the assumption is that similar vectors point to same direction, and different vectors, dissimilar vectors, point to different direction. Yeah, of course, orthogonal vectors means they point separately. This is not as severe as the opposite one. Opposite one is like boy and girl, you know, like separate. This one may be like cat and house. It might be orthogonal. So one cool thing about OpenAI embeddings is that they actually made their embeddings normalized such that the magnitude of each of these vectors, like A and B, the magnitude of these vectors becomes 1. Okay, they normalize the embeddings, which means that the cosine similarity can just be approximated by the dot product. So this dot product here can be done very efficiently with GPUs. You can just do a parallel compute and then just sum it up. So this cosine similarity is very fast. And you can use cosine similarity to find out the vectors that are most similar to your query. Any questions for this?
If the embeddings are normalized, how do you have something similar to what you first introduced? What embedding is, like the example you gave of the distance between two similar pairs of words.
You're talking about the first diagram I showed here, is it?
Yes, yes. If it's
Okay.
normalized, how do you do it?
So this is not OpenAI embedding, but if it was OpenAI embeddings, it will look like this.
Yes.
This is your center, and then this part here will be like cat, kitten. And then, so all of the embeddings will lie on the unit circle. This
Yeah.
embedding here would be dog. And then maybe at the other side here, you have houses.
No, I mean like the second example, when you walk on the same direction from king to queen, but you do a vector addition to men, you cannot get women, right? Cannot get women.
Yes, so we lose out on that.
Okay.
Yeah, so this is what I wanted to discuss also. So OpenAI, in order to make the cosine similarity be computed faster, they normalize their vectors. This increases the amount of compute that they can do in like 1 second, because you can do more dot products as compared to dot product divided by the norm of the vectors. Okay, but what you lose out is you might lose out stuff like this at the bottom. So Terry, what you say is a very pertinent point. You lose out on stuff like this because how can you walk along the unit circle, right? You can't really walk like that. So you lose out on this kind of things. So it's a trade-off. Yeah, and in fact, if we just do everything in the unit circle, you can see, maybe I can just do a bit of the discussion now. You can see that actually there's only so much things you can clutter at the side, right? Like eventually you actually can express things in a more constrained way, because like rather than just varying the range and the degree, you only can vary the degree now, which also means that a lot of things will be clustered together and it'll be harder and harder to differentiate things from each other. Okay, but luckily for most real life cases, the OpenAI embeddings of just using the angle, you can just treat it as the OpenAI embeddings just embed angle in some sense, because okay, that's a false statement to make. It's actually taking a higher dimension and then it maps into a lower dimension, which is basically the angle. So you can treat it as OpenAI embeddings kind of map things to a lower dimension, and then there can be a lot of clashes over here. But the key thing is, if your dot product is done right, if you can actually distinguish the different embeddings from each other.
I think, right, so since not angle are more important, maybe they don't, like we can't find the analogy of the second one to walking some distance, but maybe to change some angle, maybe we have a similar effect.
Okay, actually, I want to correct myself here. I just realized you can actually do this with the OpenAI embeddings. Okay, let me explain why. The man and woman, you actually can do the addition over here. You can just do the man plus woman in the vector space, in the higher dimension vector space. And then, or rather man minus woman, or woman minus man, or whatever it is, you can do this kind of arithmetic in the higher dimensional space. And then later on, when you map it to a lower dimension, it can actually preserve this semantics in the higher dimensional space. So although at the base level is just angle between the two vectors, but because this angle is between like a very high dimensional vector, you can actually preserve some form of meaning in your higher dimensions. But it's just when you map it to whether similar or not at the lower dimension, you lose out that information, but it's fine because what we are interested in is whether or not the vectors are similar. So if you were to map it down to a scalar matrix, like in this case, cosine similarity between -1 to 1, I think it's still okay to map down a higher dimension to a low dimension, because what we really want to find out is how similar they are, and the similarity is based on cosine similarity. So yeah, I would say that the normalizing of the vector would actually help out a lot more in terms of calculation. Okay, actually, let's think about it. This is something that I think you just made me think again, because you're right. Sorry, you're right. If we were to do the higher level dimension and we basically normalize it, right? I'm not sure whether we can do this kind of arithmetic if we normalize the vector in the higher dimension, because this in the OpenAI embedding, this part is normalized to 1. Yeah. So interesting question. What do you think? Do you think if we normalize the higher level vector dimension to 1, can we do this kind of?
I don't know yet. We can discuss.
Yeah, this is an interesting question. I haven't really thought of this. Yeah. Okay, let's move on because I got to go soon. So let's continue to the end. Oh, that's an interesting question actually. I should go and do some research on it. So that's how we get the similar vectors. Next up, we use like a retrieval tool. For example, we can use a vector database such as Pinecone that can store like this kind of things like key value documents. Over here, we can use this kind of vector database, Okay, we put the OpenAI embeddings onto their database, and then we can use approximate nearest neighbors. So there are a few techniques for doing that. It's like one is FAISS and one is scan. Yeah, so we can talk more about this kind of techniques when we do the memory augmentation. All right, so today I'm not going to cover this because there's not enough time left. But this top K neighbors thing can be done very efficiently by using some form of algorithms, and this online vector database can implement it for us already. Of course, you can also do it yourself. It's not difficult. Okay, but advantages of this kind of online database, of course, is that you can just query the online database without needing to store this kind of embedding yourself. Yeah. So unless you host your own cloud service, if not, if you can have like stuff like Pinecone that can do some database for you for free for like one use case, why not just use it? Okay, so these are the use cases where you can do the vector embedding and retrieval. Like what Manas showed earlier, you can talk to a document as though you are talking to a person. You can question and answer with a PDF document, like academic papers, manuals. You can basically ask it like a person, which is quite cool. You can use it to ground your language model's query such that it outputs only like reliable and factual stuff. So this has been used, I believe, by Bing search, because they also ground the search with some examples of like data sources, because you can see all the list of references that the search comes up. So this is done quite a lot nowadays. So let's move to the discussion. Okay, we have about 10 minutes. All right, let's talk about the first one first. What are the limitations of using cosine similarity to find out embedding similarity? So I think, Terry, we were talking about this just now. We lose out the kind of magnitude, okay, but at the expense, but because of doing this, we actually can compute more because we don't have to do the normalization of the vectors. We can just do a dot product. Yeah, but
Sorry, I didn't quite follow. What was the problem with losing out the magnitude again?
yeah, like for example, the case where you have a man and woman vector like that, man and woman. If you lose out on the magnitude, you might not be able to get this vector distance that accurately. Like, because over here is like girl and boy, right? Boy and girl. Yeah, if we were to normalize the vectors, like let's say we assume that this is center point, we normalize the vectors such that all of them are vector length 1. Like you may not be able to get this arithmetic. I'm not sure whether you can, so that's an open question. If you can get it, then there's no limitation. Like, can you
I
get?
think you lose out the explicit calculation, but as in, if we think of across all the data set, the multiple vectors or lines, right? What makes a man different from woman? Women have lines that the men don't coincide with. So those lines are still the constraints on how far or how close the man is to the woman, right?
Yes.
Let's say that if your data set has 100 lines or 100 vectors to define the classes, if let's say the men and women, the overlap between the lines, let's say there are 70 numbers compared to, let's say, to a bear, where it's totally not the same as a man and woman, you would expect that the intersect of the vectors between man and woman to be higher than a bear, right?
Oh, no, we're not talking about intersection between man and woman here. We're just talking about like vector arithmetic here. Like whether you can take this like W minus M, woman minus man, is it the same as girl minus boy? If we were to normalize the vectors, because you see, initially the vectors might be like that. Okay, let me give you an example. The vector of girl might be here. This might be the initial vector of girl. Let's call it G prime. And then the initial vector of woman might be here, like here. Let's call it W prime. So if we were to normalize the vector, because this is obviously too much, okay, we can normalize it to form here. This is the W prime prime, where basically it is on the unit sphere. Like this is the unit sphere from the origin, because you need all the vectors to be normalized to length 1, right? So if we were to do that, the question is whether we will lose out on the magnitude that we, because initially this is the initial vector direction. But if we normalize it to the unit sphere, we might lose out on this kind of like the direction from one point to another point in the higher dimensional space.
I see. When we were talking about the difference between D2 as well as cosine, I think the difference is just D2 is the proximity, right? Let's say in the wardrobe, you want to put stuff like your underwears and stuff in a likely space. In cosine similarity, you don't really care too much about the space, but let's say you assign each article of your clothing a particular projection, and then along that projection is whatever that's similar. So underwear will have one vector, and your bra will have another vector, and so on and so forth. Then you're saying that by doing this, you lose out in the proximity detail between the articles, is it?
Yeah, you might actually affect the semantic embedding because your initial embedding space is not a unit vector, but you force it to be a unit vector. Okay, but of course, this is for OpenAI's way of normalizing the vector. Cosine similarity does not suffer from this because we can also do cosine similarity on vectors with non-unit length, right? So that the limitation that I'm talking about over here is for OpenAI normalized embedding.
So my thought on this is unless they have a way, a one-to-one map from the Cartesian to polar coordinates in this field. If they do have such a one-to-one map, then you can preserve the structure.
Yeah, I think this is an interesting question. Not one that can be answered like just verbally like that. Need to do some math calculations to see whether it really affects.
Yes.
Yeah, but I do think it will affect. So that will probably limit a bit. Yeah, I mean, I can already see that if you only have vectors of magnitude 1, you are constrained in where you are. But the mitigating factor is the more dimensions you have, the hypersphere of that magnitude 1 actually can actually contain a lot of directions. Because if you're just talking about a circle, then yeah, you are limited by the circumference. But if you are talking about a cube, a sphere, you actually have a lot of points you can be on. If you're talking about hypersphere, you have even more points you can be on. So while it's constrained by unit length, the amount of directions that you have is actually theoretically infinite. I mean, even for a circle is infinite, but with a hypersphere, your dimensions, the potential vector directions will be exponentially higher than just.
Yes, but the notion of direction cannot be the same.
Yeah, it's a
otherwise it still
hyperdirection.
not work.
Yeah, it's a direction in a higher dimension. The direction is a n-dimensional direction.
No, I think the direction here is to go to some angle for according to some orientation, not just like a straight line. Because no matter how high dimensional your sphere is, if it's straight line, I believe it will not work.
Yep.
So that's why I talk about the transformation map from the notion of distance or the direction from a Cartesian to a polar coordinate or something.
Yeah. Okay, I think we leave that for a future time. Okay. The initial question I wanted to ask over here was actually how is cosine similarity, which is basically an n-dimensional vector, you compress it, okay, to be a scalar value, whether you lose out on any data. So from an n-dimension vector to -1 to 1, is this scalar vector sufficient to represent the kind of distinctness between vectors? Any thoughts on that? Do you think a scalar number is sufficient to tell you how similar vectors are?
Probably not.
Yeah, actually, I think cosine similarity more or less can do it, because this would tell you the more similar it means 1, right? Higher number. It's like a sort of a ranking system. So I guess using cosine similarity won't hurt that much to find out the similarity. As in, this is as
my concern is this similarity is not transitive.
It's not.
So you have A similar to B similar to C, but A and C might be very different. So with a scalar, you might not be able to capture that.
Yes, that's correct. So you lose out on some information, definitely, because you are doing a slice of the data. But whether that slice is good enough for your use case, I think OpenAI embeddings have shown that it's good enough. Yeah, so there's some limitations here. You will lose out information, but perhaps what you lose out is not that important anyway. Yeah, but anyway, I did try out the OpenAI embeddings before, and they do give some form of sometimes they return stuff that is not exactly that relevant. And that could be because the cosine similarity just makes it a very high number, but it's not exactly semantically related. So this cosine similarity issue might be related to like you are compressing a high dimension to a single 1D dimension. That's one issue. The second issue could be the way they do contrastive learning, because you need exponentially increasing amounts of samples with increasing dimension of your hidden dimensions. Yeah, so this is a limitation of both cosine similarity and contrastive learning. Yeah, so that, I mean, that's this question here actually. Contrastive learning, you need a lot more samples to do embeddings. Yeah, so actually let's talk about this question now. The benefit of this is that it can do next sentence prediction, or you can do prediction between sentences or paragraphs using the suitable objective, because the objective maximizes the distance between embeddings of sentences or paragraphs. But are there other ways to learn the embeddings between sentence and paragraphs without using contrastive learning? Yeah, you all have any thoughts on that? Okay, I mean, one thought that I had earlier on was just use the self-supervised next token prediction to learn the embeddings. Okay, but I start to see that there might be some issues with that, because if you do that, you may not exactly like compare between paragraphs that well. Probably another way of learning this, I mean, we are using like backpropagation, is instead of doing like next token prediction only, we can do something like, you know, one way we can do is like that. So this I just thought of this. Okay, so I'm quite excited about this. So y'all tell me whether you agree with this. So you can fine tune the model using this prompt. You can do sentence 1, sentence 2, or you can just do like a separator here, a separator token here, sentence 2. And then you can just put like similar, no. Yeah, so you can structure your prompts in this form where you give it 2 sentences and then you output yes or no. So this is very similar to how BERT does the next sentence prediction. So BERT has this thing called the next sentence prediction as well in their training, in their pre-training. So because GPT does not have the way to do like sentence 1, sentence 2. Now they actually use, in BERT, they use a binary predictor, like 1 if it's similar and 0 if it's not. So one way to do it is you can just fine tune using this. So this sentence 1, sentence 2 will be the input, and then this one will be the output. Yeah, do you think this can actually learn the embedding space already, just using this?
I think there's definitely a very, very obvious advantage, which is you can do different level embeddings quite flexibly, right? Otherwise, if you really train it instead of doing in context learning, let's say for some application you want to use a paragraph level, some you want to use a sentence level, some use word level, some use the essay level. Then you have to train again from scratch. But this one I can see is very flexible.
You're talking about
especially yes, especially if you want to do the hierarchical embedding. At different level of hierarchy, you want to have some kind of embedding. It's going. I think it's going to be very tedious if you train it every hierarchy of the level from scratch. But here it feels very flexible.
Yeah. So actually, I quite like this idea now. So this is the prompt, and then this is the output. Yes, no. So with GPT, I think you can actually train the sentence to give you the right embeddings just using this fine-tuning approach. So because right now the limitations of GPT is you cannot do next sentence prediction, but we can encode a form of next sentence prediction using the prompt method like what I was describing here. I just thought of this. Yeah, so thanks to y'all. I just thought of this. I think this would work. I really don't like how they use contrastive learning for OpenAI embeddings actually. I mean, it works quite well for most use cases, but contrastive learning doesn't scale well for dimensions. So I really think that there's a better way. This might be the better way.
Why does the prompt way also shouldn't scale well, right? And you might not be able to guarantee certain boundaries with the prompts.
It doesn't scale well. I just wonder whether like you can just take representative sentences like that and can scale already. Yeah. So this is something that I think we can consider, but contrastive learning definitely is something that is a problem if we have too many dimensions. So yeah, anything that can do self-supervised methods. I really like self-supervised methods. So if you can do self-supervised methods, it will be helpful. Yeah, I just wonder whether you can do self-supervised methods for sentences also. Like, I mean, right now we don't really. Oh, actually, you can do self-supervised for this. Why can't you do self-supervised for this? You just take the first sentence and take the second sentence like that. And then if it's like from the same kind of paragraph is yes. If it's no, then your sentence 2 will be from somewhere else. You can also do self-supervised for this kind of method. It's something like the next sentence prediction in BERT. So you don't have to give it all examples. You can just give it whatever it sees in the text. Okay, anyway, yep, I've got to go soon. Let's just move on. So what are the benefits and drawbacks of using embeddings, okay, for encoding semantics instead of a scalar value? So anyone want to chip in on this?
Wait, no. The fourth question, right? How can we ensure that the embedding space for the training set is generalized?
No, we're doing the second question first because we skipped it just now.
So I can see if you want to do the search, right, just now the application, then how are you going to I feel there's a concern of scalability with embedding.
Yeah, with embedding space, actually, the higher the dimension, the more information you can encode. Okay, but also it's harder to train it. Yeah.
I'm not talking about scaling with respect to the dimension, it's scaling with respect to the size of the database.
Oh, okay.
Yeah.
But
how is it going to be practical?
Oh, but even for scalar value or vector embeddings, the scaling is the same, isn't it? It's about the database.
I thought that if you calculate the similarity with scalar value, is less operation.
Oh, okay. So this scalar value is not cosine similarity, by the way. This scalar value I'm talking about is like this. Like, for example, cat, right? Now, like currently, maybe you can give it an embedding space of like that.
Yeah, I know. But
why not? What if you just do it like that? That is just some random value. Not random value, but some value. So dot can be like 0.6. So I just want to highlight this example is because we were to just use one number like that, a scalar value, it may not be rich enough to encode the higher level features between the cat and dog. Like just this number alone, like maybe house can be 0.6 or so. So we definitely need to use a form of vectors. Vectors are important. Yeah. So I just want to highlight this point in this question because if we were to just use a scalar value to represent semantics, there will be a lot of clashes. At least with vectors, you can represent different dimensions as different attributes. Yeah, Terry, anything else you want to add for this?
No, you can go to the last one.
Okay, so the last question is like that. How can we ensure that embedding space for the training set is generalizable to those outside of the training set? Hey, Dylan, you wanted to say something about this?
This is kind of like tricky. I think it's a rhetorical question because the idea behind machine learning is that if you assume that your training set and your test set, and if the actual data in the wild is totally dissimilar in distribution, then you assume that the algorithm should not be able to perform well. That's the ultimate assumption of current machine learning. So let's maybe rephrase what we know from traditional sense. Let's say that the embedding space is able to capture some information inherent to the particular class in the data set. Let's say, like, for example, we were talking about cosine similarity in the past, right? If you say you're able to specially assign a vector in your training set, right? And then all the similar stuff, let's say, all lies in this same plane. This could answer this question to some degree. So let's assume that this particular assumption holds. So if, let's say, in the wild there is a arbitrary data set that the arbitrary data that actually gets sampled within this plane, then we can assume it performs some degree of generalization. But ultimately, we have no idea of whether it's able to achieve this goal.
But I think in practice, this issue can be addressed through two means. Because we're already saying that's the case. One is training data size. For language tasks, we have a lot of data, and the second is attention. Because with attention, you know, for different, even in your test case, you know, like based on the context, you know the different, like what most likely what are the possible semantics for this particular word or this particular phrase or even two sentence. And I believe I can see that it has been addressed or at least mitigated.
Yeah, you can actually combine different inputs together to form a novel output. So that's the benefit of attention. I can see that. Yeah, and also for large language models, as what you said, the data is the web. So it's more or less the entire web is the training set. So your training and testing quite similar, especially for human language. So that I think a large data set might actually make it more generalizable because you have
Yeah,
more.
I mean, yeah, exactly. Because even for us, if we look at word, like if we assume it has some semantics we didn't even know before during our own experience, right? Then in some context, the same word might carry another totally different meaning, which I haven't seen before. Then even for us, it's not possible to figure out the meaning, right? So it's the same thing.
You need to do few shot learning. You need to, oh, this is another meaning. Okay, then I need to update my memory bank.
Yeah, so, yes, there's no way. You have to at least see some example, I think.
True. Yeah, so I think generalizability is a big problem in machine learning, and somehow scaling the data does help quite a bit. If you don't have enough data to scale, then the best bet is to encode some form of heuristics, or okay, let's not use heuristics. Machine learning people don't like it. Fixed biases. You might encode some form of fixed biases, like maybe convolutional network filters. You know, you can't sample all the images in the world. I mean, you can, but there's just too many pixels compared to words or tokens. Yeah, so in order to combat that, you can do like kind of filters to kind of constrain your kind of processing. So if you have some form of bias like this, it might help you to reduce the amount of data you need, but you need to make sure that the fixed bias is accurate and is indeed like what is really required to extract the information out from your data. So for language models, thankfully, the tokens are quite small compared to pixels. So we don't really need to do this kind of techniques to encode the fixed bias, and it can still work already.
Just one last comment. I think it's especially true for language that you cannot rely just on the generalizability, because for some word we know that it carries entirely different and totally disconnected meaning, right? How are you going to generalize for that kind of thing? It's not possible.
Yeah. Okay, if not, actually, I've got to go. But if you have anything else to discuss, I'm happy to talk more. I think today's vector embedding discussion was very good, because even I found out that like using the scaling of the vectors to vector 1, it might actually affect the vector arithmetic. I didn't think of that before you mentioned it. So thanks for highlighting that. I think we need to think about this further. Right, but if not, I would like to just conclude that this kind of applications that we do with vector embeddings that can lead to memory retrieval. Okay, let's just end on this slide. This actually can be the way to retrieve relevant data from different sources and use it to ground the context for a large language model like ChatGPT. And I believe this kind of system would be very impactful and would actually pave the way for a lot of useful products in the future. So yeah, I'm looking forward to see what other people can do with this. And this is a very exciting space indeed. Okay, I'll end here. And thanks for coming. Okay, bye.